Right, well, hello and welcome to this physics DVD. Now, this latest inset is what we're going to call, it basically is Young's modulus, even. I'm just going to say what some people call Young's modulus. And some people don't, they just go, it's for 6. Alright, anyway, so before I give you any meaning of the Young's modulus, I'm just going to put down the formula. So, Young's modulus is given by the small letter e. It's not capital, it's just a small e. Equals T times L over A times delta L. Now, we're going to go through this equation in a minute and how we came up with that. We didn't just pluck it out of the out of thin air. So if you can see that, should be a bit better. Okay, right. Hopefully you can still see me there. Yeah. Okay. So you may be asking, how did we get that equation? Well, as I'm not sure if you are doing this for the second time, you should know. It's stress over strain. Now, stress is the actual force that is held within the wire, if you can imagine it like that. But the way of force, so yeah, tensile stress. Tensile stress is denoted by force over area. Now, area you can work out in a number of ways. It could be pi times diameter squared, or over 4, sorry, or whatever way you like to work out the cross-sectional area. But you need to work out cross-sectional area, and that is tensile stress. And then it's over tensile strain. Tensile strain is just how much is being pulled. That's not a definition. That is just trying to get you to understand tensile strain. So if you can remember, strain is this stretching, which is going to be denoted by delta L over L. Now, so it's force over area divided by delta L over L, and that's because it's the tensile stress, which is force over area, over, or divided by, tensile strain. Now, tensile strain, as I said before, is a stretching of it. So, if we divide these two, you can flip this round, so it becomes force over area times L over delta L, and you multiply top and bottom to get FL over A times delta L. Now you may be thinking, well, we've got an F there, surely what's he going on about? If you can't do basic reading, what help we're going to have listening to him talk about physics? Well, hopefully you'll see where I'm going with this. The force is basically the tension, because a tension is a force. Say for example, we're going to give you, well, we'll talk about more about force in the spring section of Unit 2, but force is the tension. So they're interchangeable. So when it is represented like that on your formula sheet that you have in your book, when you sit down on the exam, you open this booklet and you get all the formulas in it and you go, yes, I know the answer, I can just put that into any equation and I don't need me, I can just give my calculator, put it down on the seat and walk out the exam hall. Well, unfortunately, Jim Bob Jones, you can't do that. So I'm just going to have to explain it a bit more for you. So force times the length over area times delta L. Now, hopefully you're sure how we got that. If we don't, you need to rewind it and pay attention this time, instead of me waffling my derriere off. So that is the equation, and that is how we got to it. But what does it tell us? I mean, why do we need to work it out? Well, to answer that question, I mean, it's an excellent question. I mean, I could interview myself and that would be, but no, that was a genuine question from me. So the Young's modulus, as you notice, we've done force over area and delta L over L. Now that's to cancel out the length and the area, which is to cancel out the volume basically of a wire. Because the thickness of a wire and the length of a wire entirely depends on like how much it's going to expand if you put a bit of weight on it. So for example, if we've got a big chunky spring, that could probably take a higher amount of weight. However, if you've got a small spring, you can't take much weight. That's why in a car you have big springs, whereas on a little swing in a park it's fairly small, unless you've got an American sitting on it. Anyway, so I'm not saying that all Americans are fat, just, yeah. Anyway, so as I was saying before, this cancels out the area and the length, so it cancels out the volume. And this can be very useful in determining what a material it is, because all materials, say copper, well, not necessarily copper, but I just give that as an example as a material. So you've got different materials, and the one material will have a certain pattern, if you can think of it, as the same material but in a larger size, because the molecules inside are the same. So it's going to react the same way, except it just reacts proportionally to the area and the extension in length, which is what delta L is. Now I said I was going to go over this formula. So T is the tension, we've already said that. E is the Young's modulus. L is the length. A is the area, and delta L is the extension from the unstretched length. Now I'm just going to give you a few tips, because sometimes in the exam hall you sit down, you get nervous, the girl next to you starts crying, and you cry, and then the examiners just go pfft, and everyone's happy, you get an A star. But sometimes it isn't the case, and you put a nasty question on the exam where they try and put it in, millimetres, and it could trick some of you out. So not necessarily the working that is the hardest bit of calculating Young's modulus, but sometimes it is the actual reading of the question. So you need to be careful of that. Okay, so that is the Young's modulus formula. So I will, you can pause it and then rewrite it down, and just because I've got to create a bit more room for myself for the rest of the video. Sorry, just checking how much I've got left. Yeah. So for the rest of the video, what we're going to talk about is how you can see what type of material it is. So we're just going to go over this very briefly. This is just, I'm just going to do stress. Stress is always on the y-axis, and strain is always on the x-axis. Now, I'm going to give you a material here that's been tested, and it's just one material. I'll compare two in a minute, and I will quickly go through this one. It's just to show you the various points on the graph and what it denotes. So, we could have a graph that looks like this. Yeah, that's right. So, Hooke's law, which is in the springs part of this tutorial, will tell you that the force applied to a spring is directly proportional to the length. So that tells you there's a constant of proportionality somewhere, and the constant of proportionality is a spring constant, or K, which is a little bit of an inside springs if you haven't watched that video yet. So that will give you a line that goes straight through the origin, which that shows. And if it goes straight through the origin, that generally indicates it's a straight line, so it's a linear relationship between force and length, as it's proportional because of the limit proportionality. So it should be a straight line, Hooke's law. That gives you an indication that Hooke's law has passed and its limit reached yeah, it's reached its elastic limit at the end of Hooke's law. Sorry, just seeing what limit it reached. So this is the elastic limit. I'm going to denote it by E. And then you've got something called yield points. Now, yield points on a wire is where there's a small increase in stress for a large increase in strain. That is when, if you can imagine when you're pulling a plastic bag, it's quite It's quite bulky. It's quite hard at the beginning, and then when you get to it going white, it goes, and then simply snaps just so quickly. That is what's happening here, except after it's done that, it carries on getting a little bit harder. So as you weaken it, you're weakening the plastic. That's called a yield point. Yeah. Sorry. Give me a second. Yeah. P is a limit of proportionality, where it follows Hooke's law, and A is just above. Sorry about that. So E, the plastic limit, is where it behaves like a wire following Hooke's law, not the elastic limit. Sorry about that. Which doesn't sound so good on a YouTube video. So yeah, the elastic limit where it's stretched and it can never be pulled back to what it was before. So yeah. And you've got your breaking point up here. That's where the wire snaps. So just go over it again. You get your plastic limit where it goes up to Hooke's law. Elastic limit where it suffers plastic deformation, so it can never be returned to its original state. You got your yield limit, so it's a small increase in stress for a large increase in strain, and then you've got your breaking point, which is where the wire snaps. So plastic is to do with Hooke's law. Elastic is where you can't go back to what it was before, and yield point, small increase in stress for a big increase in strain, and breaking point is where the wire snaps. I do need to get on a little bit with this, just so I can fit it all in. So you've got a wire here, I'm just going to go. So we might get asked, which one's brittle and which one is malleable, for example. So material X there is very stiff, and then it just seems to break without actually being able to pull it. So that could be glass, for example. And then you've got Y, which seems to be very malleable, so you can. It's got an elastic limit and it behaves like a plastic material. Yeah, whereas X doesn't. Okay, so the last bit I wanted to go over is the loading and unloading curves. So we'll keep the same graph, just to make it a bit simple. So this is a loading curve. Sorry, that's not very good, but you have to bear with my drawing. So the one going up is all one wire, so the wire going up, so the wire going down, wire going up, loading, what going down is the unloading curve. And now you may be asked a few things. So if the loading and unloading curve don't go back to the same point, it suffered permanent extension. And then the delta L between the loading and unloading curves at the bottom on the strain axis, the X, that is the permanent extension. Now you may be asking, well, there's a difference between the two wires, between the two loading and unloading curves. I'll just let you have a look at that. Now what does that represent? Well, that represents a number of things. Well, when I say number, I mean one. Given that is a number, I have just had a go at myself and corrected myself one ago. So the area in the middle is known as what? The internal energy retained by the molecules. So if you do this with a rubber band, not clap like a seal, but just stretch it and put it back together, stretch it, and it starts to get warm. And what causes that? Well, the internal energy that you're putting in is being retained by the molecules, and some of it's been lost as heat. But the internal energy is the difference in the area. Sometimes it might ask to calculate the area, so the first thing you've got to do, is normally given on a square graph, is calculate the area of one square, find the number of squares in there, and work out the area. Now what it's that was it, I was going to say. So, given this, see, I'm just going to draw a square here. This could represent any square on the graph, FYI I've enlarged it. So, F is upwards, and E is that way across a square. And F times A equals the work done in extending it. However, there is a proper formula for that. That is just a quick idea when you're trying to work out squares, and it might actually go the work done stretching it. However, the elastical energy stored in a spring is half times the tension times delta L. That is at any given point, or you could have half times K times delta L squared. And K, as I said before, is the stiffness constant, and T is the tension or the force that you're applying to it. Hopefully that's got you going a bit there. Oh yeah, sorry, when I said F times E before, that was just for a force against extension graph. That was not for a stress and strain graph. Hopefully that's caught you up to speed with everything. Again, if you need any help, just post a comment in the video and we'll see you later.